Fantastic. Okay, I still see some people trickling in, but in the interest of time, I think we will get started now. Once again, welcome to our webinar today. We're so pleased that you were able to join us. My name is Corey McLaughlin. I lead up our engagement with our sponsoring states and with the International Seabed Authority. For those of you who know me or are around the ISA, I'm sort of referred to as Corey from NORI, and it's my pleasure to be hosting you again today. We had made a priority sharing information with stakeholders, and this webinar is a continuation of the series of webinars and side events that we have been hosting over the last couple of years. Our priority is to share information with stakeholders and ensure that the information we're providing is of interest to you, to help educate and inform. And importantly, it allows us to get feedback from yourself on the program that we're doing. We continue to look for areas to improve. So please, if you've got questions or comments about this webinar, other areas you'd like to learn about, please share that information with us. We're open to feedback and would like to ensure we're providing information that's useful to you. You will see in the chat function below, we will post our email that you can send us emails to. We will also be recording this webinar for those that aren't able to make it and posting it on our website. Again, that website link will be posted in the chat, and an email link will be shared after the webinar with everybody. So please feel free to distribute the video and the recording to any colleagues or friends that weren't able to join us today. Okay, just before we get started, we'd like to turn the webinar over to our sponsoring state, that is the Republic of Nauru. We're very proud of their support that they continue to give us and of their leadership in this industry. And we'd like to just ask the acting CEO of the Nauru Seabed Minerals Authority, Ms. Francilia Adier, to say a few comments to start today.
Ladies and gentlemen, greetings and welcome. My name is Francilia Adier. I am the acting CEO to the Nauru Seabed Minerals Authority, where NORI, or Nauru Ocean Resources Inc, is our sponsored entity. It is a great honor that I deliver this brief opening remark, especially before we embark on a presentation that promises to be both captivating and also pivotal to our understanding of the environment. Before we begin, I'd like to convey our sincere thanks to you for taking the time out of your busy schedules to join us today as we listen to Dr. Michael Clarke dive into the complexities of the plume research, as well as to share some lights on how this data can deepen our understanding of the impacts of mining on our marine environment. I also like to extend our thanks to the NORI team, or the organizers, for creating this platform to address one of the critical environmental concerns regarding marine plumes, and particularly Dr. Michael Clarke for sharing his expertise and findings on this topic. I have had the privilege of attending previous sessions where Michael has shared his expertise on the different aspects of his work, including this current topic. With his wealth of knowledge, insights, and experience, this session truly offers a remarkable opportunity for learning and engagement, and I believe it will contribute significantly to our collective understanding of the impacts of mining on our marine environment. As we continue to navigate the challenges of our work, I think it is really critical that we stay informed, that we also work together towards finding solutions that will benefit both our ecosystems and economies. But anyway, without further ado, I'll hand the floor back to those that you actually came to listen to, and I do sincerely hope that you'll find this session not only informative but also enlightening. Matupa, I thank you.
Thank you, Francilia. And just before I do turn it over to Dr. Michael Clarke, I'm going to just provide two quick background slides on Nauru Ocean Resources Inc. We had a lot of questions with people registering, which we greatly appreciate. We tried where we could to incorporate within the presentations answers to those questions. Feel free, though, throughout to ask questions using the Q&A function below. We'll have 10 to 15 minutes at the end of the webinar to take those questions. We'll do our best to answer them all. But a number of questions we received early on was a little bit about the background. So we thought we'd just remind everybody who we are. And so Nauru Ocean Resources Inc. is a Nauruan registered company. It is a fully owned subsidiary of the metals company. NORI, as it's known for short, has been involved in this industry since 2011. And with the sponsorship and support of the Republic of Nauru, we became the first entity, commercial entity, to partner with a developing state to get an exploration contract. The Republic of Nauru became the first developing country to access the Reserve Bank in 2011 as part of that exploration contract. And we've had a number of firsts since then. We began our exploration and environmental work in 2012, culminating last year in the first ever integrated collector systems test since the 1970s and collecting over 4,500 tons of nodules. Our team is currently finishing up its environmental baseline as we speak, with a campaign out to the NORI-D ground. And we are anticipating and have indicated that we would be targeting a submission of an application after the July meeting next year of the ISA. We get a number of questions around the timing of our application. And we committed, after listening very carefully to the International Seabed Authority membership this July, working closely with our sponsoring state and reflecting internally. And after those discussions, we committed in August of this year to delay the submission of our application until after the July meetings next year. And we did that for two primary reasons. Firstly, it allows us to collect additional environmental data, which we feel will strengthen our application and, importantly, be able to answer some of these concerns and questions that people have and that you'll hear about today from Mike. The other thing we wanted to do was give additional time for the International Seabed Authority to finish the regulations. And they're all working very diligently towards completing those. And it's in our interest, as it is in their interests, that the regulations are completed first. And so while we have the legal ability to submit our application, it is not our preference to do so until the regulations are complete. And so we've made these two commitments, and we look forward to, over the next 12 plus months, working with you as stakeholders to share more information as we get ready to submit our application next year. So without further ado, I'll now turn it over to my colleague and friend, Dr. Michael Clarke, who will share with you today some of the new preliminary information that we've received from our environmental baseline program. Mike, over to you.
Thanks, Corey. Can you see my screen?
Yes, we can. Thank you.
Okay. Thanks a lot, Corey. By way of introduction, my name is Michael Clarke. I've been in the impact assessment industry for over 25 years. I have a PhD in environmental sciences, postdoctoral studies in marine biology from the University of London. I'm a certified environmental practitioner and a certified impact assessor with the Environmental Institute of Australia and New Zealand. Before coming to work with NORI, I was conducting environmental impact assessments for mineral mines in Indonesia. I'd like to acknowledge the incredible environmental team at NORI and the offshore teams who've been instrumental in collecting the information and the data that I will present today. I'm going to provide an update on the emerging data from a decade-long study that's being conducted on the NORI-D site in the Clarion Clipperton Zone in the Central Pacific. The data presented has been collected over 20 campaigns conducted over the last 11 years. In the latter part of 2022, we conducted test mining, that's campaign 7A, B, and C, in the NORI-D lease for the first time in 50 years. That test mining had been conducted in the Clarion Clipperton Zone. And as Corey said, we currently have a vessel on site who's conducting a 12-month post-mining campaign to quantify what the situation is like on the ground 1 year after mining ceased. This is where we are in the environmental impact assessment process. We've done 11 years of offshore campaigns. We conducted test mining last year. Over the past 12 months or so, we've been assimilating the mountains of data that we've collected during test mining and during our offshore campaigns. And we're now just in the data assessment phase. So we're now in the phase where we're actually figuring out what all the data actually means that we've collected over the previous decade or so. And as I said, we have a post-test mining survey on site as we speak. All this information will be summarized in an environmental impact statement that will form part of our submission to the ISA next year for an exploitation license for polymetallic nodule mining. This presentation focuses specifically on the benthic plume, as this is the issue that's most commonly cited as posing the most significant impact to the marine environment. Also, this is where we focused most of our efforts to this point in terms of data assimilation and data assessment. Just to orientate everybody, the site that we're talking about today is NORI-D here in the Eastern Pacific Ocean, approximately 2,500 kilometers away from the island of Hawaii, 4,000 kilometers northeast of the island of Kiribati, and approximately 6,500 kilometers due east of the island of Nauru. This is what the seabed looks like at a depth of 4,294 meters. As you can see, the seabed is dominated by a nodule bed on top of sediment. You can see evidence of bioturbation underneath the nodule bed in this video. But this is indicative of what we see in the seabed at the test field, where most of the studies that I'll be talking about today have actually been conducted. These graphics show how the benthic plume is often depicted up to this point in the scientific literature. This is from a paper by Drazen in 2020. It shows the benthic plume coming out of the collector vehicle and then immediately lofting almost vertically into the upper water layers, where the suspended sediment could be subject to the dispersive forces of advection and current movements, which could potentially disperse the benthic plume over large areas outside the directly mined site. This perception of the plume has been picked up by the popular press, and this was basically repeated in a Guardian article in 2023, where you see the plume coming out the back of the collector vehicle, lofting into these upper layers where it could potentially spread over large areas. And this description or depiction of the plume has led to statements such as this being posted, this one from the Deep Sea Conservation Coalition, that plumes of sediment will be created as mining stirs up the seafloor. So this is obviously referring to the benthic plume, possibly spreading tens of thousands of square kilometers beyond the direct mining sites. What I want to do in today's presentation is to test if such claims stand up in the face of the data that's being collected during NORI's extensive program of data collection around the plume and plume dynamics. To understand how the benthic plume is formed and behaves, NORI commissioned the Danish Hydraulic Institute, DHI, in cooperation with a number of academic institutions, including Texas A&M University, the University of Maryland, and the University of Hawaii, to implement a plume monitoring study during test mining that we conducted last year. An array of sensors were deployed to monitor the various characteristics of the benthic plume during test mining, including plume density, particle size, particle settling rate, sedimentation rate, and the sedimentation footprint dispersal. This required the deployment of a variety of sensors, including ROV-mounted bottles, which collected water samples from the benthic plume, LIS sensors mounted on the ROV, which measured the size, density, and settling velocity of suspended particles, acoustic Doppler current profilers, ADCPs, mounted both on the seafloor and attached to static moorings to measure current movements at various horizontal and vertical distances away from the mining site, conductivity, temperature, and depth sensors, CTDs, going up and down in the water column, collecting data at various depths, and also collecting water samples from within the benthic plume, and sediment trays located at various distances away from the direct mining site to measure how far sediment particles could spread away from the area from which they were mobilized. So what we see here is a graphic of test mining. We see our collector vehicle crawling along the seabed. We also had a science support vessel on site, which had another ROV collecting data and water samples. We had CTDs tow-yoing up and down through the water column constantly, collecting data and samples. And we also had AUVs. These are our autonomous underwater vehicles, which constantly circled our test field, collecting video footage and collecting samples. In addition, we had fixed moorings with ADCPs and hydrophones attached to them, and then a whole array of benthic assets that were movable, that were surrounded the test field, collecting data on sediment deposition. Here we can see the surface assets, the vessels that are included in the study. And here are some of the monitoring sensors located on the seabed, ADCPs measuring particle density in the water column, and these sediment trays that were located on a gradient at various distances from the direct mining site so that we could measure the levels of sediment deposition with distance away from the point of mobilization. In total, there were 50 plume monitoring stations established in and around the 4 kilometer by 2 kilometer squared test field, collecting data on all aspects of plume dynamics, concentration, and dispersal. This animation shows the collector vehicle moving along the seabed and creating a plume behind it. That's this yellow dot going up and down as it crisscrosses the 4 kilometer by 2 kilometer squared test field. Each of these wavy lines that you see is a sensor that's being triggered, and as it changes color, it's detecting sediment that's been mobilized into the water column. These periodic bright traces that you see in the test field are either ROV or CTDs entering the arena to collect water samples or other data. And the traces that you constantly see swirling around the test field are the AUVs, which are those torpedo-shaped autonomous vehicles that we saw in the previous slide that constantly encircle the test field, collecting data and shooting video. Predictive models have now been developed by the Danish Hydraulic Institute based on information that was collected in the field. This included plume density, plume dynamics, particle size, flocculation rates, current rates, water temperature, bathymetry, etc. This has been combined with oceanographic data that's been collected from moorings that have been deployed in the NORI-D lease continuously for over 3 years now. And we also included data on sediment dynamics that we collected during lab studies that were conducted prior to test mining. So DHI has now quantified these and other parameters and assimilated them into predictive models of plume dynamics, which can be scaled up to simulate full-scale production. This is an animation of such a model showing the generation and dispersal of the plume behind the collector vehicle as it traverses the seabed during test mining. What the seabed's observations show is that rather than the benthic plume lofting up into the upper layers of the water column, like we saw in those graphics that I showed at the beginning of the presentation, where the plume is subject to dispersal over large areas from the effects of advection and currents, that most of the sediment, and estimates say approximately 95%, forms what we call a gravity current on the seabed, which flows away from the collector vehicle under its own weight, following the bathymetry of the local seabed. And what we see here is a turbidity current that's been generated in the lab, just to show how a turbidity current moves across the seabed and doesn't loft into the upper layers of the water column. This is how it's been described by Thomas Peacock from MIT. The turbidity current is a lateral gravity-driven spreading of the sediment-laden water under its own weight away from the collector tracks. And it's not a case of the sediment being passively carried away by the background ocean currents. And this is pivotal when we're looking at how far a sedimentation footprint will spread on the seabed. The formation of a gravity current shouldn't really have been a surprise to anyone attempting to develop a predictive model, as it was predicted from results of lab experiments using sediment from the Clarion Clipperton Zone as far back as 2020 and in subsequent lab testing in 2021. And we've now have field verification of the formation of a turbidity current from at least 3 independent studies. In 2023, the GSR studies, which were monitored by Thomas Peacock's group in 2022, and then also studies conducted in shallower water in the Mediterranean. Graphic A depicts how the plume exits the collector vehicle on the seabed, staying just a few meters above the seafloor and dispersing away from the vehicle as a gravity-driven current, which largely follows the contours of the seafloor as shown here in graphic B. Only a very small fraction of the finest components of the plume, and MIT estimates somewhere between 2 and 8%, actually lofts into the upper water column, where it has the potential to be dispersed by advection and ocean currents over large distances. This video shows the formation of the low-lying density current as it exits from the back of the collector vehicle. As you can see, the plume is not lofting to fill the whole frame of the image, as we would expect if a density current wasn't being formed. The vast majority of the suspended particles form this low-lying layer just a few meters above the seabed. This footage is taken from an ROV following the collector vehicle as it collects nodules and produces a benthic plume. And you can clearly see the lights on the top of the collector vehicle, and the vertical extent of the gravity-driven current is clearly demarked just a few meters above the seabed. I've included this graphic to illustrate just how important it is to have an understanding of plume dynamics and sediment behavior before engaging in any kind of speculation on how far the sediment may spread and how extensive the impacts may be. Prior to conducting test mining, we developed a sedimentation footprint model based on our limited understanding of plume dynamics at the time. As you can see, this preliminary model predicted that the plume would spread extensively outside the 4 by 2 kilometer square test field in a northwesterly direction, carried on the prevailing currents that we expected at this time of year. However, when we rerun the model after test mining and we updated our assumptions and updated our parameters to reflect the sediment behavior, plume dynamics, and current dynamics that we actually observed in the field at 4,000 meters, a very different sedimentation footprint emerged that was much smaller than our original predictions. So this raised the questions as to why was the sedimentation much smaller than our original models predicted? And we narrowed it down to 4 key reasons. First of all, the cut depth was much lower than we'd assumed in our original model. Our engineering partners, Allseas, have been very, very adept at creating nozzles that can pick up the nodules while leaving the majority of the sediment on the seafloor. As a result of that, the volume of resuspended sediments was significantly lower than we'd assumed in our original model. Sediment aggregation or flocculation was a lot quicker than we assumed, leading to fast settling. And the turbidity flow is more influenced by the bathymetry of the seabed than it is by the water movements and currents at over 4,000 meters. Now that we have calibrated the model using our newly found understanding of sediment behavior and plume dynamics from our field studies, we can use this model to predict the depth of sedimentation at various distances away from the direct mining area. And we're going to verify the model predictions using seabed video footage and thorium-234 tracing techniques, which I'll describe a bit later on. So what we see here is the verified sedimentation footprint from test mining. Most of the sedimentation is actually confined within the 4 by 2 kilometer test field. This orange area on the outside, which is the spill outside the test field, is very, very low levels of sedimentation, 0.05 to 0.1 millimeters, so less than 1/10 of a millimeter. And this is a very conservative model at the moment. This is still being verified, and our modelers seem to think that once we get more verification from various samples that we took on the seabed that the extent of this footprint will actually contract even more. So in addition to modeling the dispersal of the benthic plume and the subsequent sedimentation footprint, we also collected a very extensive database on the biological component of the environment in and around the test field. Box cores, multi-cores, ROV and AUV video transect deployments were conducted during the baseline studies, as well as immediately before test mining started and 10 days after test mining ended. In total, 346 box core and multi-core sample sites were established in and around the test field, and over 240 kilometers of ROV and AUV video transects were conducted. And that's what you can see on this graphic. These efforts have generated thousands of samples, tens of thousands of specimens, and hundreds of thousands of data points on which our assessments are based. This data has been collected by some of the most accomplished academic institutions and marine contractors in the business, including the Natural History Museum from the United Kingdom, the National Oceanographic Centre in the UK, Leeds University, Florida State University in the US, Texas A&M, Allseas, our engineering partners, NIWA, which is the scientific arm of the New Zealand government, and also CSIRO, which is the scientific arm of the Australian government, just to name a few. I like to show this video just to show how precise our sampling has been, and also how adept our offshore teams are at collecting data. What you see here are 2 tracks from our collector vehicle, obviously after the area has been mined. These tracks are 2 meters wide with a 2-meter space in between them. We had a request come in from one of the science teams as to whether we could actually get a sample from this 2-meter wide area between the tracks, because they wanted to see if the compaction forces from the caterpillar tracks actually caused any impact to the infauna in the sediment. Compare that to this area that wasn't compacted between the tracks. When this request came in, I personally didn't think it was possible to get a sample from this area. And when I consulted with a few of our academic advisors, they didn't think it was possible either. I did give the challenge to Claire Dalglish, our offshore chief technician, and she's been in the business 20 years. She is a commensurate professional, and I was flabbergasted when she actually sent this video back to me a few days later. As you can see, the multi-core has been deployed right between the 2 tracks. And when you consider what is being done here, we've got a 1 meter square asset on the end of a 4-kilometer long wire attached to a moving platform, which is the vessel at the surface. And we are able to deploy that asset to within a 2-meter wide space on the seabed. So absolutely phenomenal expertise from our offshore teams. And just to prove that that wasn't a fluke, here is the same feat repeated with the box core. So I'm very, very confident with the quality of the data that we've collected and the quality of the sampling that's being conducted offshore. And hats off to our offshore teams, and good luck with campaign 8, which is being conducted as we speak. So now that we have a verified model of the sedimentation footprint and the spatial and temporal biological data, we can start to assess the magnitude and extent of the impacts that the benthic plume and sedimentation may have on the benthic biota. And we can do this by overlaying the sedimentation gradient onto the spatially and temporally distinct biological data and testing for significant differences in key metrics in space and time across major biological groups. For example, we've tested for statistical differences in key metrics such as species richness, abundance, and diversity, both before and immediately after test mining. As we mentioned, we also have a vessel on site at the moment collecting data at 12 months post-test mining so that we can see if trends in biological responses are preserved after the first year. So let's start by looking at the extent of the sedimentation footprint after almost 4 months of continuous test mining. We collected video footage of the seabed in and around the test field to verify our sedimentation model. These images show what the seabed looks like in the directly mined areas within the tracks of the collector vehicle at 10 days after the cessation of mining activity. Let's first look at this area in this white box we have here. So this is in the directly mined area. These lines that you can see are the mining tracks. We're going to look at some images taken from within the tracks. These are the tracks you see here and the spaces between them. So within a directly mined area, this is what we'd expect to see. We can see the imprint of the caterpillar track. The nodules have been removed, and we're seeing heavy deposition of sediment. Again, this is the track. This is the other track. This is the 2 meter space in between them that we can sample with the multi-core. And then again, our 2 tracks, our 2 meter distance between them. And here we can see some megafauna that's re-entered the area. Still looking at the directly mined area in this white box. But now let's look at images that are taken from between the tracks. So this area here between the caterpillar tracks. Our sedimentation model is predicting that we're going to get sedimentation levels in excess of 60 millimeters in this area between the tracks. As I said, this is a very conservative model, and we're still verifying it with some field sampling. We actually think that this is probably less than 60 millimeters, but that's still to be confirmed. This is what we'd expect to see. The nodules are actually still in place, and you can just make out the profile of the tips of the nodules, but it's quite hard to see under these heavy levels of deposition. Again, we can see just make out the profiles of the nodules under this level of deposition at these 3 separate sites. And again, in this one. Let's move now slightly to the east in this area here. And we're right on the margin of the directly mined area. So this is the last track at the border of the directly mined area, and it's approximately 120 meters from where these images are taken. Our modeling predicts that we're going to get 20 to 30 millimeters of deposition in this area. So this is about 120 meters away. Again, we think this is a conservative estimate. Here you can see the profiles of the nodules quite clearly underneath the blanket of sediment. They're a lot more defined because we've got a lot less deposition in this area. So this is what we'd probably expect to see at 2 to 3 centimeters of deposition. Moving to the east a little bit more now, we're probably 300 to 400 meters away from the edge of the directly mined area in this white box. We're going to be looking at images from this transect. We actually have tens of thousands of images of the test field and the surrounds and hundreds of hours of video footage. So this is just the selection. Our modeling suggests that we're getting 2 to 5 millimeters of deposition in this area. And that is borne out in the images. As you can see, the nodules are very well defined now, even though they're completely covered with sediment still. But the fact that it's such a thin veneer of sediment means that we can quite clearly see the nodules underneath. But again, these nodules will not be available as attachment or habitat for sessile obligate organisms. So for all intents and purposes, the nodules are still not available as habitat, even at 2 to 5 millimeters of deposition. Let's move out a little bit further now to this area. We're now maybe 500 meters away from the directly mined area. We're going to be looking at images from these 3 spots here. Our modeling predicts that we're getting 1 to 2 millimeters of deposition at 400 to 500 meters away from the directly mined area. And now we're getting a very different perspective of the seabed. We can see the nodules. There's lots of nodule surface area exposed. We can see that there's bioturbation occurring underneath the nodules. And with the naked eye in most of these frames, it's actually hard to see that there's any deposition occurring at all. It's a bit more evident in this bottom one. And this could well be because this is a low point. And don't forget, the gravity current is following the bathymetry of the seabed. We now move up to this area where our model predicts we're getting 0.05 to 0.1 millimeters. So that's less than 1/10 of a millimeter. And this is about 1,600 meters away from the direct mining area. We're going to be looking at these 3 points. And very difficult to see any evidence of deposition in these frames. 0.05 to 0.1 millimeters of deposition. Very hard to distinguish this from the frames that we're getting from our control site. This is the control. The actual control site is off the image. It's 4 or 5 kilometers away from the direct mining area. These images are taken from these 3 points. And as we can see, very similar from what we saw in the previous images, lots of nodule surface area exposed and plenty of evidence of bioturbation in the sediments below the nodules, and some megafauna in this final one. As a secondary method to measure how far the sedimentation footprint spread from the directly mined areas, we pioneered this technique of tracing the radioisotope thorium-234. Now, thorium-234 occurs naturally in the water. This is a natural radioisotope that's present in much higher concentrations in the water column than it is in the sediment. And this work was inspired by work that had been done on the Deepwater Horizon project in the Gulf of Mexico. And we'd like to thank the researchers from Eckerd College for pioneering this study. This is the first time that this technique has been used to quantify mobilized sediment deposition. I'd like to acknowledge Brian O'Malley from Eckerd College for his excellent and pioneering work on this topic. So because the thorium naturally is in much higher concentrations in the water column than it is in the sediment, what we find is that when we mobilize particles of sediment by running the collector over the seabed, the longer a particle is mobile in the water column, the more thorium it actually attracts. And we can use this as a proxy to measure how far a particle of sediment has actually moved laterally from the point of mobilization. So if we measure the thorium content of the sediment within 3 weeks of test mining, because thorium has a half-life of approximately 24 days, we can actually use the thorium concentration as a proxy for how far that sediment particle has traveled. And what we find is the natural thorium concentrations in the sediment are all around 2 GPM per gram as the baseline condition. And then if we go back 3 weeks post-test mining and resample the thorium content of the sediment, what we find is that the sediment in the tracks has a slightly elevated thorium concentration. And this makes perfect sense because as the collector vehicle has gone over an area, it's mobilized sediment particles, they've gone up into the water column for a short amount of time, scavenged a small amount of thorium, and then fallen back more or less to the same point from which they were mobilized from. If we go out 200 meters, we find slightly elevated thorium levels. And again, this makes sense. Those particles have been mobilized by the collector vehicle. They've traveled laterally 200 meters. They spent longer exposed in the water column, scavenged more thorium, and then been deposited. And then at 0.5 kilometer, 500 meters, we get a peak in thorium concentration. And that's because these particles have spent the most time suspended in the water column. Interestingly enough, is when we sample at 1 kilometer away, it's back down to background levels. And what this suggests is that this outer boundary of the sedimentation footprint lies somewhere between 500 meters and 1,000 meters. And this corresponds very well with our modeling, which predicts that this boundary between this very low concentration of 0.05 to 0.1 millimeters of deposition is right around this 500 to 400 meters away from the direct mining site. So we've got good collaboration between our video imagery, our thorium tracing, and the sedimentation modeling that's been done by DHI. So what we have now is what we like to see when we're conducting really robust, good science, is that we have multiple lines of evidence that support a number of findings. We have the laboratory studies that were conducted before test mining that predicted the formation of a turbidity current based on the properties of the sediment that were collected from the Clarion Clipperton Zone. We have multiple field verifications that a turbidity current does actually form in the field. We have our sedimentation modeling that's been verified by seabed images. We also have seabed sampling of the biota, which I'll talk about in a minute. And we have our thorium-324 tracing. So what findings are supported by these multiple lines of evidence? Well, the findings that we found from our studies, but these findings have also been found from the GSR work that was conducted by Tom Peacock's group at MIT, is that the sediment plume is low-lying. The sediment plume initially forms a turbidity current, and this is a gravity-driven spreading of the sediment layer under its own weight away from the collector tracks. And it's not the case that the sediment is being passively carried away by the background ocean currents as those early images depicted. MIT specifies that 92 to 98% of the sediment initially stays below 2 meters above the seabed. And as a result, as we have shown in our seabed images, there is very heavy local deposition in the vicinity of the collector tracks. These last 2 points are particularly relevant because we'll talk about the shortcomings of some of the plume modeling that's been done to date. And these last 2 points are particularly relevant to that. Evidence suggests that the dispersal of the gravity-driven turbidity flow is more influenced by the bathymetry than it is by the ocean currents. And also we demonstrated that global current models are a poor indicator of benthic current dynamics. And that's why our initial sedimentation footprints that we did before we'd actually collected any data was not an accurate prediction of what we saw in the field. So just take note of these last two bullet points. So now that we have information on the how far the sedimentation footprint spreads, and we also have information on how the benthic biota responds to different levels of sedimentation, we can start to think about our impact assessment. An industry standard way of assigning impacts to different areas is to assign zones of impact and zones of influence. This is taken from the International Institute for Sustainable Development, where they recommend identification of zones of high impact, zones of moderate impact, and zones of influence. This approach has also been adopted by the Western Australia Environmental Protection Authority in their technical guidance to environmental impact assessments of marine dredging proposals. This is probably the nearest industry that we have to deep sea mining. And this approach has also been adopted by the Great Barrier Reef Marine Authority when predicting impacts of urban runoff onto the Great Barrier Reef, and coming up with a management plan for those impacts. And a lot of this approach is based on work that's been done by CSIRO, the scientific arm of the Australian government. And we've actually engaged CSIRO to help us take a similar approach to our ecosystem-based management plan for our deep sea mining project. So the first stage to assigning zones of impact and zones of influence is to actually define what you mean by zones of high, moderate impact and zones of influence. So this is adapted from the guidance in the Western Australian EPA dredging manual. So a zone of high impact would be defined as an area where you've applied a pressure to a number of biological metrics that you're monitoring, and you see what we call a press response. So this is a sustained suppression of those biological metrics. And we'd expect to see a response like this in the direct mining areas where we've either removed nodules or we've covered nodules with a very thick layer of sediment, and for all intents and purposes, they're not available as habitats to nodule obligate sedentary organisms. In the zone of moderate impact, you would apply, this will be an area where you apply a pressure, and we see an initial negative response in the biological metrics that we're measuring, but given time, they actually come back and rebound back to where they were in the pre-mining condition. And we'd expect to see a response like this in areas where we're getting this light sedimentation of 1 to 2 millimeters. We've still got plenty of nodule habitat exposed. We're still seeing evidence of bioturbation underneath the nodules. And it'll be really interesting to see if these patterns of the pulse and press responses are actually maintained at 12 months after mining. And that's what the team that's currently out on the campaign 8 is collecting data to investigate that as we speak. And then the zone of influence is an area where maybe your predictive model says that there's likely to be some level of sedimentation, but you're not actually seeing any negative responses in the biological metrics that you're measuring. So the biological metrics that we've measured are summarized in this table. So we're measuring ecological and biological metrics over a number of taxonomic groups: sessile megafauna, motile megafauna, macrofauna on the nodules, macrofauna in the sediment, meofauna on the nodules, meofauna in the sediment, and different forms of foraminifera. And we're going to be measuring these metrics across a whole range of different deposition levels. And the key ecological metrics that we're measuring for the baseline, for T0, which was immediately after test mining, and T1, which is at 12 months, are things like total abundance, relative abundance, species composition, and species diversity. So the whole idea is to statistically test these metrics with the control, both the spatial control and the temporal control, which is the baseline compared with T0, T1, etc. We also have metrics that measure changes in ecosystem functions, such as oxygen production and carbon assimilation. So what the preliminary data is pointing to is these are the kind of responses that we're seeing in various parts of our sedimentation footprint that was developed during test mining. We're expecting to see 0 environmental or biological responses in response to less than 5 millimeters of deposition, and that would constitute a zone of influence where our modeling is saying that we may get very low levels of deposition here, but we're not seeing any responses in our environmental and biological metrics that we're measuring. A zone of moderate impact levels of deposition of 0.5 to 2 millimeters. In these areas, we saw a suppression in some of the biological metrics that we were measuring, particularly ones associated with megafauna and nodules. When we go back and resample after 12 months, it'll be really interesting to see if this has been a sustained press response and we see a continued downward trajectory in these metrics, or if they actually have come back to their pre-mining condition. If there is a continuous response on a downward trajectory, then we may expand the boundary of the zone of high impact to include the green zone. And then in the zone of high impact, we get these press responses where for a prolonged period of time, we see a depression in the ecological and biological metrics that we're measuring. The main take-home message from this particular image is the distances that are involved. So the distance between the directly mined area where we're seeing press responses and the zone of influence where we're expecting to see no responses from the biological metrics that we're measuring is in the order of a few hundred meters, 500 to 600 meters. And just out of interest, the reason that this sedimentation footprint is kind of skewed to the east is because it has been developed by the sediment flows following and forming a turbidity currents and following the contours of the seabed. And we actually have some raised relief here on this western side, which has kind of pushed all the sediment towards the east. So this is really important because some of the claims that have been made by some of the modeling that's been done up to this point, that sediment will settle over 1 millimeters deep at 10 to 15 kilometers away from the direct mining areas, are simply not supported by the data that we've collected. If we go back to this diagram, we're seeing we're getting less than a millimeter at about 300 or 400 meters away from the direct mining area. And this is because this modeling hasn't taken into account the formation of a turbidity current and how turbidity currents follow the contours of the seabed. Similarly, we look at this modeling commissioned by the Deep Sea Mining Campaign, which predicts that the benthic sediments, it's quite clear here that this is a benthic plume simulation, that the benthic sediments mobilized on the NORI-D lease will travel up to 200 kilometers, settling way outside the boundaries of the lease. We've clearly demonstrated that the majority of the benthic plume settles within a few hundred meters of the mining site during our test study. And there's two fundamental problems with the underlying assumptions of this model. They've modeled the sediment particles being released at 8 meters from the seafloor, and this in no way accounts for the formation of the gravity-driven turbidity current, which contains up to 98% of the plume particles and constrains them to within 2 to 3 meters of the seafloor. Also, they've used open drift software, which relies heavily on global current models to model particle dispersal. And as we've clearly demonstrated, global current models in themselves are poor indicators of what's happening to the benthic currents at 4,000 meters. Similarly, this is not an accurate depiction of how the benthic plume exits the collector vehicle. It doesn't loft into these upper layers the way this image depicts, where it can be subjected to advection and current movements and potentially disperse over large areas. If we wanted to do a more accurate depiction of this graphic, where we've added some scale, it would look something like this. Each of these squares that you see here represents 100 square meters. And when this is drawn to scale, we can see that the benthic plume barely registers in terms of its vertical loft at the bottom of the image. Because of these misconceptions about how the plume would behave, then that's led to statements such as this. Plumes of sediment will be created as mining stirs up the seafloor, obviously referring to the benthic plume, possibly spreading tens of thousands of square kilometers beyond the mining site. This is from the website of the Deep Sea Conservation Coalition. I will give them the due. When I presented this at an ISA side event about 2 weeks ago, within 48 hours, they'd amended the language on their website. It now states that the plume could disperse over tens to hundreds of kilometers beyond the mining site. Still not consistent with the data, but a step in the right direction. What our data does support is these statements that were made by MIT after the GSR field studies, that their measurements showed that the vehicle created a dense plume of sediment in its wake, which spread under its own weight, known as a turbidity current. As it gradually dispersed, the plume remained relatively low, staying within 2 meters of the seafloor, as opposed to immediately lofting higher into the water column as has been postulated. This is quite a different picture of what these plumes look like compared with the conjecture. Thomas Peacock also goes on to say modeling efforts of deep sea mining plumes will have to account for these processes that we have identified in order to assess their extent. And that's exactly what hasn't been done in this model. This model does not account for the development of the gravity-driven spreading of the sediment-laden water under its own weight away from the collector tracts, and incorrectly assumes that the bulk of the sediment is passively carried away by the background ocean currents. That is not what the primary data that we've collected on site is indicating. So to wrap up, upcoming focus for the NORI Environmental Programme, we are going to coordinate the science studies from Campaign 8 and see if those press and pulse responses that we're getting in the biotic indicators actually persist after 12 months, so that we can refine our zones of high, moderate impact and our zones of influence. We're going to use the emerging data and modeling to address the remaining key issues, including concentrations, dispersal, and impact of the midwater plumes. Some of the primary data that we've got and some of the modeling has come up with some really interesting information about the dispersal of the midwater plumes that will challenge some of the conjecture and speculation that's been tabled to date. Similarly, we've got good emerging information on the chemistry of the midwater plume and its potential to have impacts on fisheries. Again, this will challenge some of the conjecture that's been tabled on that issue. We're developing a noise model, the first noise model for a complete nodule collection system, and we're working very closely with Allseas to develop some very innovative mitigation and attenuation measures to minimize noise production. And only when we've resolved all these issues can we have an informed discussion on the potential impacts for biodiversity. And that is basically a summary of our work program over the next 6 to 12 months. So with that, that's the end of my presentation. We may have time for a few questions.
Thank you, Mike. Fantastic presentation. Thank you, everybody, for sticking with us through that presentation. It's always a good sign when you add participants over the course of an hour rather than lose them. So congrats, Mike. You've obviously got the attention of everybody. To Mike's point, we do have a lot of questions. We've done our best to type some answers. So if you've asked questions, check out the chat link. We've tried to respond a little bit in writing there. We've got over 20 questions outstanding. So if people are willing, we're willing to stay on a little bit later, and we'll do our best to answer the questions as we go through it. Please bear with us. I have tried my best to compile questions that are similar together. So if you don't hear your exact question, we've tried our best to lump it in with others of similar nature. With that in mind, Mike, maybe the first question we had from a number of individuals was asking about the midwater plume. I know today you focused solely on the benthic, but would you maybe just give people an idea about how we will determine the depth of the midwater plume? And you mentioned at the end that we'll be coming back with some additional data on that, but that would probably be a good place for us to start.
Yeah, look, so we are still currently developing the midwater plume models. So really at this stage, don't want to comment too much on that until, don't want to speculate until we've got data to support our position. But what we do know, as I said in the presentation, is that our engineering partner, Allseas, have been very, very good at creating nozzles that are capable of picking up the nodules and leaving most of the sediment on the seabed. So the amount of sediment that's being actually transported up the riser pipe to the surface vessel has been minimized, and we have a few other mitigation measures that we can implement into the system to minimize that midwater plume. So when that modeling is available and when we have good insight into how far we can reduce the concentration of that plume, then we'll be in a much better position to answer those questions.
Fantastic. Thanks, Mike. a question around the zones of influence, and a question was asked, why was 2 millimeters identified as an area of high impact?
Because at 2 millimeters, what our model is showing is that the nodules are completely covered with sediment. So that nodule surface area has been taken out of, it's basically not available for nodule obligate organisms to inhabit. If that 2 millimeters of sedimentation is removed, either by water movements at the seabed or by macrofauna activity, and those nodules become available again, that nodule surface area becomes available again, then that area may actually move from an area of high impact into an area of moderate impact. And that's going to be the exciting part of going back after 12 months and 24 months to see if there has been any sediment movement and if those zones of impact can actually expand or contract.
Fantastic. Thanks again, Mike. Okay, we've had 3 or 4 questions talking about, Mike, the scalability of the current modeling. And so as we move towards operation, the size of the collector increases. So maybe I'll answer a few questions and then I'll turn it over to you. So we had a number of questions around slope and the impact of the plumes on different types of slopes. So maybe what I would just start by saying is we chose a test mining field that was representative of where we wanted to prioritize the first collection of nodules. And so we operated and tested the collector system at slopes of up to 4 degrees. We will then develop and design our mining plan that we'll submit to the ISA that will operate within those parameters. And so if we wanted to increase the slopes that the collector works on, we will need to test those again as well. And so I think, Mike, then this gets into a couple of similar type questions, which is around how confident are we in the ability to scale the modeling that was done on the plumes at a collector that increases? So people have noted that we used a smaller collector, 6 meters wide, and they've asked what would happen. And then the other question they had, Mike, was, is the testing that was done in that zone reflective of our expected mine plan? So would the mine runs, for example, be longer? So maybe you could just answer those types of questions.
That's a really good question. So basically, now that we know now that we have resolved the plume dynamics, now that we know how the gravity current is formed and how it flows and how it follows the contours of the seabed, it's quite easy to scale that up. You know, if we have a bigger collector, then we've got a greater mass balance going into the collector vehicle, and we know how it behaves, and we can scale that up. And that's what DHI are doing now. So they're taking the lessons they learned from the prototype collector test. We now have good understanding of how the plume is formed and how the gravity current is formed behind the collector, and we're confident we can scale that up. And the other thing is now that we know that the density current follows the contours of the seabed quite closely, we might be able to use that in our mine planning to control which areas the sediment is channeled towards, which could be of benefit to us. In terms of the when we go into production, what we are anticipating is that the runs will be much longer, obviously, and you know what that means for the mine plan. We'll have to establish that in terms of the the modeling that DHI has done. So I can't really answer that question at this stage until we get the models and the responses from DHI.
Excellent. Thanks, Mike. We had a question around the sediment traps that were used. And the question is, do deposition rates on these match the sedimentation model?
That's a good question. I would have to go back to the modelers and see what the agreement was between the sedimentation traps and the model. As I say, I'm given an overview of what the models say in terms of the technicalities of those models. We'd have to go back to the modelers to get that. I can't answer that question.
Okay, no, that's fair. Thank you. Mike, we've had a number of comments also around dissolved particulate trace metals within the benthic plume. What, if any, data or monitoring was done? And do you have a timeline on when we think we'll be ready to release some of that data?
Yeah, all that data was collected. So as I said, we had Niskin bottle sampling at various depths, and we did sample within the benthic plume. That is currently being analyzed, and we don't have that data yet, but we are expecting it to be, we are expecting it pretty soon, but I don't have that data at this point.
Okay, thank you for that. We also had a question about the speed of the collector, and was the video that you showed with the collector moving representative of the speed that the collector would be traveling during operations? And so the answer generally is yes. During the test mining, we tested a variety of speeds for the collector and did a number of maneuvers to test its technical capabilities. But what we did then find was we optimized the speed for collection and to minimize environmental impacts. And so we will be able to reference those speeds, and the plumes that were generated at those times were fed into the model. So to answer that one, we've still got a number of questions outstanding. So if people want to just bear with us for a few more minutes, we'll try to get through a couple more. Mike, I will just go to data. We had a question around the amount of data that we have collected, and a question around where it will be made available and will it all be public. So maybe you could talk a little bit about the amount of data we're collecting, where it goes, the requirements of the ISA, those sorts of things.
I'd probably like to point that one to Lee if she's willing to answer it. She's our data guru. Lee, are you for that one?
Yep, sure, absolutely. Thanks, Mike. So yeah, all of our data it will be made publicly available. So we are obligated to provide all our data to the ISA under our contract with the ISA for NORI-D. And we are making efforts to get that to deep data. And our academic partners are also freely available to publish any of their data that they actually collect during any of these operations. So any of our baseline or any of our collect test operations and the monitoring. So it will also be made publicly available that way. Obviously, the speed at which we've collected this data over the last 18 months means we are collecting it, assimilating it, interpreting it, getting the publications ready, and also submitting to the ISA. So it is coming. It just takes time for us to get it out into those public repositories and to the regulator. But I can say that we absolutely will be making it all publicly available.
Thank you, Lee. Mike, this one may be maybe a little bit difficult, but we had a couple of questions talking about other examples of EIAs and their current the plume modeling that they have done. And they're asking if one of the assumptions that was maybe done by some of those models that you referenced earlier, what was sort of the big mistake or something that wasn't taken into account? And they were asking if there were a couple of things that our data is showing that those models didn't consider that led to the variance in what they were predicting and the data that we now have.
Well, I think the big thing that we demonstrated is that as the plume comes out the back of the collector vehicle, it forms the density current, which basically stops the vast majority of the sediment lofting into the upper areas where it can spread over very large distances. And it was only, GSR noted this when they did their collector vehicle test a couple of years ago, and it was noted by in Thomas Peacock's work. We also predicted this when we did laboratory work using sediments from the CCZ, that a turbidity current would form. And that wasn't accounted for in some of the modeling that was done up to this point. And that's why we get these huge predictions of how far that benthic plume was likely to spread that just aren't supported by the data.
Great. Okay, thanks, Mike. In the interest of time, I know we've gone 15 minutes over. We've had a number of questions just around the process of collecting the nodules itself. And maybe I'll just briefly touch on that, and then we can close off. So we had a couple of questions about how the nodules are collected, what happens to them. So they will be collected by the collector using the Coanda effect, which generates airflow, allowing the nodules to be lifted They go into the collector where they go into a hopper. The majority of the sediment is separated from the nodules, and that sediment is then discharged out the back. The nodules are then taken up the riser pipe to the vessel with some residual sedimentation. And then, as Mike mentioned, that residual sedimentation and the return water will be released at a depth to be determined in the midwater based on our upcoming midwater results. We've had questions around the efficiency of the collector, the speed. Again, those are data points that we aren't disclosing at this point. Just for full disclosure, though, that type of technical information will be included in our test mining report that will go to the International Seabed Authority for them as well. And we are committed to preparing a test mining report on the collector test that we did last year that we will make publicly available as well, which will get into further details around the collection test, the different aspects of it, and some of those results. So rest assured, more information on that is coming. I apologize. I think we've probably got 5 or 6 questions that were unanswered, but in the interest of time, we probably will end there. Also, those questions were very technical. So we do have your name. I would encourage you, please look at the chat, send us an email if you'd like to have a conversation with Mike or Lee afterwards. We're happy to get into that level of detail. And please feel free to send any comments you have to the website or to the email address that Rachel has put in the chat. We're happy and interested to continue the dialogue with you. In closing, again, we will send an email out after this webinar with a short survey. We would greatly appreciate any feedback you have on that. We will send out the link of the recording once it is available and posted. Please share it with your friends and colleagues. And just a shameless plug, we will be doing a second webinar in a couple of weeks' time with our head of sustainability. She will be talking about some of the life cycle analysis that we've recently had done, and also carbon sinks, which are topical at this point for a number of stakeholders. And we'll continue the webinar series early next year as well. So thank you again for your time today. We greatly appreciate the questions. Our apologies if we didn't get to all of them. Please do follow up with us so that we can speak to you one-on-one. Have a great day, and we look forward to having you join us again in a few weeks for the next webinar. Thanks so much.